Hello everyone, welcome to Discover Automation. In today's video, we're going to demonstrate an automatic bottle filling line project. The PLC program for this project has been developed using RSLogix 500 and is being simulated with RSLogix Emulate 500 through RSLinx Classic. If you'd like to explore the complete project, including the PLC program, documentation, and source files, you can find everything in the GitHub repository linked in the video description. With that said, let's dive into the project and see how it works. Now, let's move over to the HMI. The HMI for this project has been developed using Wonderware InduSoft Web Studio, now known as AVEVA Edge. We're currently on the home screen of the HMI. This project consists of three main screens: the home screen, the configuration screen, and the alarm screen. Once we enter the system, the home screen provides a complete visualization of the bottle filling process, allowing us to monitor the entire system from start to finish in real time. Here, you can view the current system mode, system status, total bottles packed, rejected bottles, production rate in bottles per hour, start and stop controls, an emergency stop button, and several other process indicators. Now, let's take a quick look at the configuration screen. The configuration screen is mainly used for process configuration and testing. From here, we can manually simulate faults, adjust the bottle fill level set point, define the required production quantity, reset the hour meter, and clear the production KPI records. Within the manual fault simulation section, we can trigger several predefined faults, including a cap absent fault, a leaking bottle fault, a capping arm jam fault, and sorting arm jam fault. For the capping arm jam fault, two different scenarios can be simulated: a retract jam and a complete jam. Similarly, the sorting arm jam fault also provides two fault conditions that can be used to verify the system's fault handling and recovery logic. Below that, we have the bottle fill level set point, which determines the target filling level for each bottle. Next is the bottle output set point, where we specify the total number of bottles to be produced. If this value is set to 0, the system will continue production continuously until it is manually stopped. To modify any process set points, reset the hour meter, or clear production records, you must first log in as an authorized user using valid credentials. Now, I've already created an authorized user account, so let me quickly log in. Once we're logged in, let's configure the process parameters. I'll set the bottle fill level set point to 95 and the bottle output set point to 1. This means the system should produce a single bottle, fill it to approximately 95% of its capacity, apply the cap, and finally transfer it to the packing section. Now let's verify the complete process in real time. I'll navigate back to the home screen and press the System Start button. There we go. The system has successfully started. As you can see, the in-feed conveyor begins moving immediately, and the system enters the transit mode, transporting the bottle toward the filling station. Once the bottle reaches the filling station, the bottle presence sensor detects its position and signals the PLC to stop the conveyor. The filling valve is then energized, allowing the bottle to be filled until the configured fill level set point of 95% is reached. Once the bottle reaches the configured fill level of approximately 95%, the PLC de-energizes the filling valve, stopping the filling operation. The conveyor then transfers the bottle to the capping station. As soon as the bottle arrives, the capping station bottle presence sensor detects its position and signals the PLC to initiate the capping sequence. The capping arm extends, places the cap onto the bottle, and then retracts to its home position, completing the capping operation. The bottle is then conveyed to the sorting station for the final quality inspection. At the sorting station, the cap presence sensor verifies whether the bottle has been successfully capped. Since the cap is present, the bottle passes the inspection successfully. The sorting mechanism allows the bottle to continue on to the outfeed conveyor, where it is transferred to the packing line, completing one full production cycle. Since the bottle output set point was configured to 1, the system has automatically stopped after producing the required number of bottles. Now, let's increase the bottle output set point to 10 so the production line can continue running. Next, we'll test one of the fault handling scenarios by enabling the cap absent fault. The fault has now been activated. Let's start the system once again and observe how it responds. The production line is now running, and we'll wait for the bottle to reach the capping station. When the bottle arrives, the bottle presence sensor detects it and initiates the capping sequence. However, because we've intentionally enabled the cap absent fault, the capping arm performs its normal movement but is unable to place a cap on the bottle. Now, let's see how the system handles this situation at the sorting station. As the bottle reaches the sorting station, the cap presence sensor checks whether a cap has been successfully applied. Since no cap is detected, the bottle is identified as a rejected product. The in-feed conveyor is temporarily stopped, allowing the reject mechanism to operate safely. The reject puller arm extends, picks up the faulty bottle, transfers it into the reject bin, and then returns to its home position. Once the reject cycle is complete, the production sequence is reset, and the system resumes normal operation, ready to process the next bottle. As the production process continues, the system updates its performance indicators in real time. The bottles packed and bottles rejected KPIs are updated automatically after each completed production cycle. In addition, the bottles per hour value is recalculated and refreshed every 1 minute, providing a live indication of the production rate. Now, let's reset the cap absent fault and move on to the next fault scenario. I'll disable the cap absent fault and enable the leaking bottle fault. The fault is now active. Let's restart the process and observe the system's behavior. As the bottle arrives at the filling station, the bottle presence sensor detects it and initiates the filling sequence. However, because the leaking bottle fault has been enabled, the bottle is unable to reach the required fill level. The filling valve remains open until the preset filling timeout expires. Once the timeout is reached, the PLC recognizes that the desired fill level has not been achieved and generates a leaking bottle fault alarm. Instead of continuing through the normal production sequence, the bottle is immediately marked as defective. The bottle bypasses the capping operation entirely, passing through the capping station without stopping. It then proceeds directly to the sorting station for rejection. After the bottle reaches the sorting station, the reject arm extends, picks up the defective bottle, transfers it into the reject bin, and returns to its home position. With the reject cycle complete, the system resets and continues processing the next bottle in the production line. Now, let's move on to the next fault scenario and test the capping arm jam fault. I'll enable the capping arm jam fault and select the retract jam condition. With the fault configured, the system is already running, so let's observe the sequence. As the bottle reaches the capping station, the bottle presence sensor detects it and initiates the capping operation. The capping arm extends normally and successfully applies the cap to the bottle. However, because we've enabled the retract jam fault, the capping arm is unable to return to its home position after completing the capping operation. The PLC waits for the arm to retract within the configured timeout period. When the timeout expires without receiving the home position confirmation, a capping arm retract jam alarm is generated. At this point, the production sequence is paused and manual intervention is required. The operator must inspect the mechanism, clear the fault condition, and reset the alarm before production can continue. After the alarm is reset, the capping arm successfully retracts to its home position. With the mechanism back in its normal operating state, the PLC resumes the production cycle. The bottle is then transferred to the sorting station, where it passes the cap inspection successfully before continuing on to the outfeed conveyor, and finally to the packing line. Now that we've reset the alarm, the retract jam fault is automatically cleared. Next, let's test the second fault condition by enabling the complete capping arm jam fault. The fault has now been activated. Let's return to the process visualization and observe the system's response. As the bottle reaches the capping station, the bottle presence sensor detects its arrival, and the PLC commands the capping arm to begin the capping operation. However, because the complete jam fault is active, the capping arm is unable to move from its home position. As a result, no cap is applied to the bottle. The PLC continuously monitors the arm movement and waits for the expected position feedback within the configured timeout period. When the timeout expires without any arm movement, a complete capping arm jam alarm is generated and the production sequence is halted. At this stage, the operator must manually inspect the mechanism, clear the fault condition, and perform an alarm reset before the system can resume operation. After the fault has been cleared and the alarm is reset, the capping arm is commanded once again to perform the capping operation. This time, the arm extends successfully, applies the cap to the bottle, retracts back to its home position, and the production cycle continues normally. The bottle then proceeds to the sorting station, passes the inspection, and is finally transferred to the packing line. Now, let's test the final fault category, the sorting arm jam fault, also known as the reject puller arm jam fault. First, I'll enable the sorting arm retract jam fault. Since the reject arm only operates when a defective bottle reaches the sorting station, we also need to create a reject condition. I'll enable the cap absent fault so that the bottle will be identified as a rejected product during inspection. Now, let's return to the home screen and observe the complete sequence. The bottle passes through the filling station as normal. Because the cap absent fault is active, no cap is applied at the capping station. When the bottle reaches the sorting station, the cap presence sensor detects that the bottle is missing its cap and marks it as a rejected product. The reject puller arm extends normally and successfully picks up the rejected bottle. However, because the sorting arm retract jam fault is enabled, the reject arm is unable to retract back to its home position after picking up the bottle. The PLC waits for the reject arm to return within the configured timeout period. When the timeout expires without receiving the home position feedback, a sorting arm retract jam alarm is generated, and the production sequence is paused. The operator must manually inspect the mechanism, clear the fault condition, and perform an alarm reset before production can continue. After the alarm has been reset, the reject arm successfully retracts back to its home position. With the reject mechanism restored to its normal position, the PLC resumes the production cycle and continues processing the remaining bottles. Now, let's move on to the final fault scenario, the complete sorting arm jam fault. I'll enable the complete sorting arm jam fault. To ensure that a bottle reaches the reject mechanism, I'll also enable the leaking bottle fault, which will cause the bottle to be rejected during the production cycle. Let's return to the home screen and observe the system's response. As expected, the bottle reaches the filling station, but is unable to achieve the required fill level because the leaking bottle fault is active. After the configured filling timeout expires, the PLC generates a leaking bottle alarm, marks the bottle as defective, and transfers it directly to the sorting station for rejection. When the bottle arrives at the sorting station, the PLC commands the reject puller arm to remove the defective bottle. However, because the complete sorting arm jam fault is enabled, the reject arm is unable to move from its home position. The PLC waits for the reject arm to begin its movement. When no movement is detected within the configured timeout period, a complete sorting arm jam alarm is generated, and the production sequence is halted. At this point, manual intervention is required. The operator must inspect the reject mechanism, clear the fault condition, and perform an alarm reset before production can resume. After the fault has been cleared and the alarm is reset, the reject arm successfully extends, removes the defective bottle, returns to its home position, and the production sequence continues normally. Before we conclude, let me also demonstrate how to reset the hour meter and the production records. We'll navigate back to the configuration screen. These functions are available only when an authorized user is logged into the system. To reset the hour meter, press and hold the Reset Hour Meter button for 5 seconds. Similarly, to clear the production records and KPI data, press and hold the Reset Record Data button for 5 seconds. Once the hold time is completed, the selected data is reset successfully. Finally, let's verify the operation of the emergency stop, one of the most important safety functions in the system. The production line is currently running under normal operating conditions. Now I'll press the emergency stop button. As soon as the emergency stop is activated, all equipment is immediately de-energized. The conveyors, filling valve, capping mechanism, sorting mechanism, and every other output are safely turned off. This ensures that the entire production line comes to an immediate and safe stop whenever an emergency situation occurs. After the emergency condition has been cleared, the system cannot be restarted immediately. First, the operator must press the Alarm Reset button to acknowledge and clear the emergency stop condition. Only after the alarm has been reset can the System Start button be pressed again. As you can see, the production line resumes normal operation and continues the process safely. And that brings us to the end of this automatic bottle filling line demonstration. If you'd like to explore the complete PLC program, HMI project, documentation, and other project resources, you'll find everything in the GitHub repository linked in the video description. If you found this video helpful, please leave a like and share it with your friends or colleagues who are interested in PLC programming and industrial automation. And if you haven't already, don't forget to subscribe to Discover Automation for more real-world PLC, HMI, SCADA, and industrial automation projects. Thanks for watching, and I'll see you in the next video.